Hello students, today we are going to study the topic what imperfection in solids. Okay, so what does this word imperfection means? Means the defects, okay, in the solids. Okay, so we have seen about the solid, it is of two types, crystalline and amorphous. Okay, so this crystalline and amorphous, they have got long range and short range arrangements. Okay, so and that is why they are known as solids, because it gives them some shape to them, isn't it? So now, when we are talking about that, how does this structure, when they are being formed, is that totally perfect? Sometimes defects can occur, okay, because it is formed by the process of what? Crystallization basically, isn't it? So what happens here? Actually, by the process of crystallization, okay, here in solids, first what happened? Small crystal starts forming, okay, and these small crystals, what it is happening, how this process of crystallization is taking place, okay, we are heating it, applying some energy to it, okay, and as the result what, or some energy is being applied, okay. So what happens? These small crystals, they again form what? The whole lattice. How they form? Suppose if we are taking the example of NaCl, okay, this NaCl, okay, will join with another NaCl, okay. It will again, because if we are saying NaCl, it is not that only one atom of Na and one atom of Cl and that it is forming the crystal. No, they will join, isn't it? And they will form a group, thereby forming what? Small crystals. Here also what happens when they are being formed, okay, separately some other also can join together to form, okay, small crystal. Now what happens? This group and this group starts joining, and thereby leading to a what? Formation of a whole lattice. And when they are forming the lattice, naturally there will be defect, okay. When these are also combining with each other, there can be defect, okay. So while formation of the small crystals also, defect can arise. While formation of a total whole lattice also, defects can arise, okay. So here we are going to study about those defects, okay. So when we are talking about this imperfection in solid, the defects basically they are divided into two, and basically those two are point defects and line defects, okay. When we are saying about point defect, it is the deviation to a point, okay, or an atom. It means it is small, very small, isn't it? Now, if we are talking about line defect, it is deviation in entire row of a lattice point. So when we are defining it, specifying it, when we see about the point defects, it mainly will arise where? In the small crystals, isn't it? Because it is dealing only with the deviation to the point or the atom. But yes, when we are going to the line defects, it will be the defect in the entire row of the lattice. So here basically line defect will be seen in the whole big lattice structure. And as the result, here in class 12 you have to study basically of what? The point defects, okay. Now coming to the point defects, okay, point defects are of three types, okay, stoichiometric defects, impurity defects and non-stoichiometric defects, okay. So first we are going to study about what? Stoichiometric defects, okay. So stoichiometric defects, basically they are what? Intrinsic in nature. They are thermodynamic defects, means the defect caused due to heat, okay, and they don't disturb the stoichiometry of that lattice. How? Okay, here I am going to explain you, okay. Actually what happens, this point defects, okay, this forms the stoichiometric defect of point defect, okay. It is of two types, vacancy defect and interstitial defect, okay. Here we are seeing, when we are seeing about the stoichiometric defects, okay, they don't affect the composition of the lattice, okay. What happens? Composition is not affected at all, okay. It means what the substance is, it will remain that only, it will not become another substance, okay, and their arrangement also remains similar in this, okay. So here when we are going to study vacancy defect and interstitial defects, first vacancy defect, okay, what happens in this, you can see the atoms over here, okay, the particles are arranged, okay. In this vacancy defect, an empty space comes out. It means a vacancy is being created, okay. Actually, these stoichiometric defects are due to thermodynamic defects. When it is heated, when these molecules are heated, this defect is caused. So what happens might be at that time, what happens, this particle tries to escape or it escapes out, okay, but it does not affect the arrangement of the other particles in that, isn't it? Okay, they are similar in nature, their composition, this composition of these particles are also similar. It will not change, its property will remain similar. Getting? So here what happened in this vacancy defect, a lattice site is vacant. It means what? In this structure here, the space becomes vacant. From here that particles escapes out while forming the crystals as heat is being produced over there. Heat is being used over there. Okay. Now, if a vacancy defect is caused, what happens? Its density will become less. Naturally what happens? The particle is moving out, its mass become less, resulting in low density. Okay. Now, next point, it develops due to heat. I said to you, here this is caused due to heat. This is an intrinsic defect, defect caused inside this structure, okay, and here it is due to heat, so thermodynamic effect, okay. Now, interstitial defect. Here we have seen about the vacancy defect, the particle is missing, but here we are saying that here's one more particle adds up in the interstitial site. Okay, here also the composition is not affected, the arrangement is not affected, but yes, one additional particle comes and takes over the space where it is empty so that it can accommodate inside it. Okay, but the property doesn't change, okay, the property beta remains similar here also and here also, okay. And here this particle just enters into the interstitial site and gets accommodated over there, and naturally if the particle is being accommodated, what happens, it mass of that will increase, resulting in what? The increase in the density. And as the result, what happens here, there is increase in density, but yes, the composition remains similar, the properties remain similar, and even the arrangement remains similar in this case of stoichiometric defect. Here we have studied about the stoichiometric defects of non-polar solids, isn't it? Now we are going to study about the polar solid, the stoichiometric defects in the polar solid or the ionic solids. Okay, here also it is of two types, vacancy defect and the interstitial defect. When we are talking about a vacancy defect, okay, in this ionic solids or the polar solids, we study about what? The shorty defects. Okay, here actually what happens, we are seeing this here, the ions present over here, okay, are electrically neutral. It is a stoichiometric defect. Naturally the ions will be what? Neutral in nature. The number of positive charge will be equal to the number of negative charge. But what happens in this shorty defect? Okay, what happens in this, you can see here whole lattice is placed over here, but here two vacant spaces we are seeing. From here Cl is missing and here Na is missing. It means one positive charge and one negative charge is missing, creating a vacancy defect. But yes, when we talk about the charges, there is no difference in the charges because one positive charge is missing and one negative charge is missing. Now also it is in under neutral form. So in which type of solids or the compounds we can see this case of defect, the shorty defect, that is in which the element size is what? The atom size is what? They are similar in nature, like we are seeing of Na and Cl. Okay, no such big difference is there. Okay, potassium and chlorine, that is water, potassium chloride, NaCl, okay, cesium chloride. Okay, here the size is similar. Okay, but yes, as there is vacancy created over here, naturally what will happen? Its mass will become less. As a result, it will create what? Low density in that ionic solid. Okay. Now, coming to Frankel defect. Okay. This is an interstitial defect. Here, when I am saying it is interstitial defect, then we are seeing in this what? Yes, iron we can see in the interstitial side. But what happened over here? This positive ion has moved from here to the interstitial side. So this is a special defect we can say, in which we can see what? The vacant space also, as well as in the interstitial sides the particle is present. Okay. Here the main property of this kind of solids is that what? The cation, it means the positively charged ion, is smaller in size. Okay. And the anion is larger in size. Okay. So best examples which we can see is what? Zinc sulfide, silver chloride. Okay. Zn2 plus ions, the silver ions. You can see here the size is too small in nature. Okay. But when we talk about the density, okay, density will it change? Here the vacancy has been created. Okay. And here it is in the industry. Naturally it has just moved from here. So no effect in the density. Density remains similar and the charges also remain similar. Here also it is electrically neutral. Coming to the second defect, okay, that is the impurity defects. Okay, it means some impurity is present in that solid. Okay, where it is present in its structure. Okay, so what happens in this? We can take the example of what? NaCl in a molten form. Okay, this molten form of NaCl, it is in the raw form. It can consist of some impurities. Okay, like it contains some amount of what? Strontium chloride, SrCl2. Okay, so what happens here? This strontium has got +2 positive charge. Okay, and sodium has got +1 positive charge. So what happens? This strontium occupies in one of the space of where sodium is present. Okay, but sodium has got 1 positive charge. Strontium has got 2 positive charge. So 2 sodium will be removed out. Because you all know that here what? It is electrically neutral in nature, isn't it? So number of positive charge will be equal to the what? Number of negative charges. Cations, the charges which they are consisting will be equal to the charges of the anion to become electrically neutral. As the result, what happens? We see here and here 2 places Na will be missing, and in one place it will come what? Sr2 plus, thereby just balancing those Na plus ions. And as here a different particle has been added, okay, this is a impurity defect. Okay, you can see this impurity defect like SrCl2, it can be cadmium chloride, CdCl2 and silver chloride. Okay, these are some of the examples of what in the impurity defects. Now coming to the non-stoichiometric defect only, that is the metal excess defect. But previous one we have studied that yes, that was also a metal excess defect, that was due to the deficiency in what? The anions, the metal excess defect was there. But here which we are going to study here, metal excess defect is due to the presence of extra cation in the interstitial site. Okay, so this metal excess defect is caused due to what? Due to the defect in the crystal structures we have studied already. Now going in details of the metal excess defect due to the presence of extra cation in the interstitial site. Actually, why does this happen? Come on, take the example of zinc oxide. Okay, when we heat it, it will break up into Zn ions and half O2, and 1 electron will be just released out. Okay, so now here what happens in this, actually in the crystal structure we are seeing what? This oxygen which is being released out, it comes to the surface and it combines with another oxygen to form what? O2. But what happens to this Zn2 plus? It remains as it is, isn't it? So it goes and occupies in the interstitial sites, and as the result we are seeing here the excess is due to the extra cation, this extra Zn2 plus present over here, and this is the metal excess defect due to the presence of what? Extra cation in the interstitial site, and it is a non-stoichiometric defect. Now coming to the metal deficiency defect. Okay, this is also a non-stoichiometric defect. Okay, and this is due to what? The defect in the crystal structure. Okay, earlier we have studied about the metal excess defect. Now we are going to study about what? Metal deficiency defect. Okay, when we are saying metal deficiency defect, it means here there is some deficiency of the metal, isn't it? Here what happens in the compound, the elements are not present in a proper ratio. I'll say for a minute also there is a difference. Like for example, if we see this iron oxide, okay, iron oxide is mostly found as FeO, we know that, but here Fe is only 0.95%, okay, and here oxygen is 1, it should be 1:1, isn't it? But here it is what? 0.95:1. So here there is a deficiency of this metal, okay. Now, mostly this iron oxide ranges from what? Fe 0.93, okay, to what? 0.96, okay, but it is not 1. So here perfect ratio we can't say 1:1 in this, as we are writing the formula FeO. It should be 1:1, but it is not. Okay, slight difference is there. Actually, what happens over here? Fe2 cation is missing. Okay, naturally here Fe2 plus is there because you can see the formula is here what? FeO, isn't it? So here Fe2 plus cation is missing, which is made up of what? That missing this Fe2 plus is now what? Fulfilled by Fe3 plus ions. Okay, here this is also found, and this is a very minute quantity, and as the result the formula remains FeO only. Okay, so in this class we have studied about all the imperfections in the solid, the defects in the solids. Okay, hope you might have understood it. Good day.